Hi, my name is Aaron Wang. I am a rising senior at the University of Washington, and I will be presenting about my work on the ROB, the Reproducible Open Benchmarks. And my mentors are Professor Shishei Su and Heiko Mueller. So let's start with some background on what the ROB is. So the ROB was inspired by the paper, The Machine Learning Landscape of Top Taggers. So what this paper did was they compiled and compared multiple top tagging models together to compare the performance of different models in top tagging specifically. So the problem that Heiko saw this before was that this took it took a significant amount of time to compile and organize and evaluate all of these models together. So the goal of the ROB is to provide a platform that automates the collection, execution, and comparison of these submissions of participants in a benchmark. So now let's go over how the ROB works. So first, a coordinator of the benchmark for workflow. So what the workflow does is it defines what input data is needed. So what input data they put in, what kind of code they need. The users then provide the code that satisfies the steps of the workflow. And then the ROB processes all the users' code. And then using the validation code provided by the coordinator, and the front end displays the results. So for example, in the top tagging example, the coordinator would provide the input data. So in this case, this would be the validation set for the top tagging data set. And then the coordinator provides two steps for the user to submit. So that would be the pre-processing step. So that's their pre-processing code and their tagger. So which is their already trained top tagging model. And then lastly, the coordinator would provide a result evaluation task, which is displayed in the front end. So what this is a validation script that displays the end results that we want to see. So for example, if we're comparing the AUC of these models, this validation script would display the AUC. So in sum here, the user provides the code to pre-process the input data, and a top tagging data in which the inference on the data is drawn, and then the code that the coordinator of the benchmark provides evaluates the user's inputs for the AUC. So right now, the current problem with the ROB is it's quite hard to use, mostly because the ROB currently requires participants to package all the submissions into Docker containers. And for people that are more unfamiliar with coding, this has a steeper learning curve. So in order to solve this issue and to increase ease of use in general, we wanted to implement support for the commonly used Jupyter notebooks. So we want to allow users to submit their implementations directly as Jupyter notebooks rather than Docker containers. But there's a few problems. Jupyter notebooks are executed cell by cell. So unlike a Python script, it's not the entire script that's run. It's every cell of a notebook is run individually. And then it cannot be run like a Python script and called in the command line in that same way. So the issues we need to solve is we need to find a way to define parameters within a Jupyter notebook. We need to be able to parameterize the Jupyter notebook so that we can run this same notebook with new parameters without needing to open the Jupyter notebook itself. And then we need a way to run the Jupyter notebook within the ROB without needing to open the Jupyter notebook editor at all. So our solution was to look into a tool called Papermill. So what Papermill does is it parameterizes and executes notebooks in its entirety. So this is a very convenient way. So to make Jupyter notebooks into an object that can be run directly from the command line and executed completely. So how does Papermill work? So users are required to define one cell in the Jupyter notebook with the tag parameters. So the author of the Jupyter notebook would have to have one cell that designated to all the parameters that they want to use and all the parameters that they could possibly change when they run the notebook in the future. For example, in the picture below, there's two examples, so alpha and ratio. So when you run it on Papermill, you can enter new values of alpha and ratio outside of the Jupyter notebook itself, and the new values of alpha and ratio will update into the Jupyter notebook. So what all the user needs to ensure is that the entire notebook runs with no errors, and that any parameters that they want to use and change are within this cell that is tagged parameters. So then users can then execute the notebook using the Papermill execute notebook function. So the inputs that you need to use are the path to the Jupyter notebook that you want to run, path to an output notebook. The output notebook is a new Jupyter notebook that is created with every output of every cell already written into the notebook, and then a dictionary of parameters that you want to use. For example, for example, in the case of the last slide, with the parameters alpha and ratio, as you can see in the example script on the side, the parameters are in a dictionary with alpha equals 0.6 and ratio equals 0.1. So pm.execute notebook can be run within the command line like a Python script, in which you can change the values of alpha and ratio so that the Jupyter notebook can be run with different values of parameters. So then we need to find a way to implement Papermill into the ROB. So the ROB runs on something called steps. So there's currently two. There were two step types before I implemented something called a notebook step. So what these steps do is that they take defined workflow inputs and user inputs and then runs the function. So this is the direct script that takes the inputs to the workflow and executes them. So then to make Jupyter notebooks work with the ROB, I need to make a new step. So this is called the notebook step. So I implemented this notebook step by making a subclass of the workflow step class, and then using Papermill to parameterize any inputted Jupyter notebooks and then execute them. And then next, I need to implement a worker. So what a worker does is that it executes steps of a given context. So what this allows the ROB to do is it allows different steps to use different step types. For example, if you had a workflow that wanted to take a training step as a Jupyter notebook and then a validation and then a pre-processing step as a Python script, you would call a Python worker first for the pre-processing step, and then you would call the notebook step using the notebook worker. So these were the two main tasks I needed to complete to ensure that the Papermill worked with the ROB. And then lastly, I needed to create another worker that was able to run the Jupyter notebooks, run Jupyter notebooks that are contained within Docker containers, because originally the ROB is used was made so that complete workflows within Docker containers could be run. The main problem with Jupyter notebooks within Docker containers is that we would need to write another script to install all the requirements within the Jupyter notebook that was already within the Docker container. Yeah. So then let's go into how to actually use this piece of software. So first we can talk about the Hello World demo. So the Hello World demo is the most basic demo that we have for the ROB. And it's mostly used to test that the ROB is working and give a basic introduction to the steps that you need to do to set up and use the ROB program. So the inputs are data, so it's a list of names in a text file. And then we have a Jupyter notebook that reads a list of names and writes greetings to an output file. So the user provides a list of names, and then the coordinator has provided a Jupyter notebook that reads this list of names and writes the greetings. For example, if the names were Aaron and Shay, and then the greeting was hi, then this program would output hi Aaron and hi Shay. So this is an example of how the ROB is able to run to take submissions and run on them within the program. So due to the time constraints, I won't be able to give a live demo, but we have a demo online at the GitHub repository below. So the main gist of it is you want to create a ROB user, create a hello world workflow using the very convenient ROB workflow functions. Start the hello world demo run, and then you want to submit your notebook and data from the command line, and then retrieve the results. And lastly, as my contribution to the ROB, I added something called the jet flavor demo. So this was inspired by the paper Jet Flavor Classification in High Energy Physics in Deep Learning. And this is using the data set from the paper that can be accessed from the UC Irvine portal. So what this paper did is it used multiple LSTM models, feed-forward network, and an outer RNN model to train that is trained on the jet flavor data set, which is a vertex and track-based data set with lots of features. So there's track features, vertex features, and higher level features. And then what the paper decided in the end is that using all three features using all the features resulted in a higher AUC and better performance in the models. And as you can see in the figure in the right, there are lots of different types of models that had to be trained and compiled, which takes a significant amount of time. So if this was implemented into the ROB, users could just simply submit their architecture to the ROB, and the ROB would run this architecture, train the model, run the inference on it, and then give you a result without without the user needing to have multiple Jupyter notebooks and multiple different ways of organizing their data and graphs. So the workflow we have here that I made here is that a user would input their model architectures. So this would either be as a Python script or as a Jupyter notebook. Similarly, the user would input their preprocessing script and their training script as a Jupyter notebook or as a Python script. While the workflow coordinator, so the person that sets up this workflow, would provide their training and validation data sets, and then a validation script that provides AUC, and then ways of plotting the AUC and training curves. So in summary, I was able to implement the Jupyter notebooks into ROB as a form of input. I created demos. I created multiple types of demos using Jupyter notebooks for use in ROB. And the demos I made are for a quick-draw data set. This is a data set made by Google for image classification, the jet flavor data set, which I just went over. I added to the existing top tagging data set. And then we have a simple tutorial using the MNIST data set. So now any user can download these demos and then add to this comparison, this competitive comparative form using these demos. And then I have the demos in the repositories below. And then I have my code for the flow for the backend below also. And then in the future, I will be presenting this at the ML4Jets conference on June 7th. And then some future work that I need to do is I need to fix the Flask web server so that users are able to submit Python notebooks within a intuitive browser form, and also as in addition to being able to submit from the console. Thank you. And are there any questions?
Anyone have any questions for Aaron?
Hi, yes, hello.
Okay.
Yes.
Small question on the Jupyter notebook. You mentioned you used another program, I guess, that allow you to run the notebook as a script.
Mm-hmm.
Did you try, or was it, I guess, not feasible for what your project aimed for, that you can make the Jupyter notebook a script with one of the file options? You click on file and you can convert your notebook into a script, although I'm not sure if it would have worked for you.
So I did think of that, but that didn't work 100% of the time when I tried it. So we thought the better solution was to use this package because it also allowed you to parameterize the notebook also. So that was my solution to it. There could be more convenient solutions, but we found that this one worked the best.
Awesome, good.
Hi, yeah, so my name is Ed, and I'll be presenting my work on expanding the utility of RECAST workflow for particle simulations. And then my professor was also Tsai. So first of all, what exactly are particle simulations? So particle physics experiments at the LHC are extremely expensive. So instead of running a new experiment for every new model, we can instead simulate collisions of these real particle simulations, collisions at the LHC and the Atlas detector to test new possible theories and new possible models for particle physics. And so, however, full particle simulations would also simulate how these final products would interact with the detectors, and then the analysis of the detector data that would actually happen at the LHC and Atlas in order to get the same output from both the actual experiment and the simulations. However, truth level simulations ignore this in order to reduce complexity. So this sacrifices accuracy and completeness. Instead, it allows for a lot faster simulations and a lot easier to use and make simulations. And so this allows for high turnover of different models to test before doing a full run simulation. However, still these truth level particle simulations are still very hard to make. So analysis could take a couple of years to make sometimes. So another method for increasing this is by using something called RECAST. So basically, RECAST, instead of starting in each model from scratch, you can repurpose old analyses. So for example, here on the right, you can see you have some model A that you're looking at, and you can recast it and look at model B instead. So the underlying standard model that model A is applied to on top stays the same for both models. And so you can just recast this model A into a slightly different model B and look at the output. And so, yeah, you only need to estimate the effects of the new physics because the standard model calculations are all going to be very similar. RECAST allows you to modularize and preserve these new analyses for future work, even after the author is gone. And so the work I actually did was called RECAST-wf. And so this is a Python package, a command line tool for creating these fast workflows to test and reproduce truth level simulations. And so it creates these workflows that can be carried out by a program called Yadish. And so basically outputs this YAML file, which Yadish reads and executes. And so RECAST-wf manages a series of these sub-workflows, and it handles the passing of input variables and files and outputs. So basically, there's a tons of different simulation tools that you need to do a full truth level analysis. And we want to make it easier to run all of these components together automating the passing of input files and downloading and installing these. So it uses Docker to run each of these programs as its own container that is pre-installed and correctly configured. So you don't need to actually download each of these programs and configure them. And so this allows you to easily reproduce someone else's work because you don't have to worry about their own environment, their own computer, messing with the results because everyone runs it in the same container. The eventual goal of this project would be to run it on Viana supercomputer cluster via some sort of web interface. And so this way, nothing needs to be installed locally. You don't need to install Docker or RECAST-wf. You could just use this web interface and upload configuration files and then have the computer run it for you. And so then I'm building on previous work done by Vlad and Alex for this fellowship. So one of these programs that has its own Docker container is called MadGraph. And so this is the main tool for doing simulation collisions. So it simulates the initial particle collision. And so it allows inclusion of a new model of physics. So this is a UFO. So this is where you would include your beyond standard model physics. And so you can see over here, you can input some sort of model, and then you also define your Feynman diagrams and different model parameters. So you see the Feynman diagram for this example, and then also configure different parameters. For example, the mass of new particles that you're adding, or the different coupling constants and other parameters. And so we improved this MadGraph integration in RECAST-wf in order to support these custom models and parameters. And another step is after the MadGraph, you have to do a showering step. And so there's two different programs, Pythia and Herwig, which we implemented that can do this. And so the job of showering step is to combine the parton level events that MadGraph produces into a hadron output, which is what the actual physics is. And so Pythia does this showering only for MadGraph events. So it's designed to be used in conjunction with MadGraph very easily and can be actually run directly from MadGraph. Meanwhile, Herwig is a different alternative, which also has its own event generator like MadGraph, but then also includes the showering. And so we only used it to do the showering after MadGraph. But however, Herwig does not support beyond standard models like Pythia does. So you need to actually import this into Herwig in a different way. And so previously the Python was directly integrated into the MadGraph subworkflow, but now we've modularized this, creating a new showering step, so that you can swap in and out different showerings such as Herwig. And then of course we added Herwig support just for the showering. And so here we can see an example of two different workflows using Pythia and Herwig. So on the left, you can see the Pythia. And so you start out with the generation. And so you have sort of input card like we showed for MadGraph. And then you have the custom model for MadGraph on both steps. And then you do the showering. So there's a Pythia. And you take some sort of input. And then same for Herwig, also takes an input. But then Herwig also has to import this same model that you gave to MadGraph. And then you could do some sort of analysis. So we use MAD analysis. This allows you to do the recasting, and this will produce some sort of output, for example, a confidence level. And so here's the code that we worked on to add the custom parameters for MadGraph, and then also adding the custom UFO models into MadGraph. And then we also separated the Pythia into this new showering step. And then also supported a custom Pythia card inside the Pythia subworkflow. And then we also added the Herwig subworkflow, as you can see here. And that also takes the similar inputs, and then also the new model that Pythia does not need. And then here we see the Pythia subworkflow again. So in order to actually test this implementation, we applied it to the mono SPV model. So basically, it's a new standard, beyond standard model proposal, which includes dark matter. Dark matter is this new theorized particle which explains astronomical observations. And so it's predicted that there's up to 5 times as much ordinary matter. There's 5 times as much dark matter as is ordinary matter. So this is a huge problem in physics, and this is one possible answer to it. And so the mono SBB would allow for dark matter detection at the LHC via the proton-to-proton collisions they do. And then this is a reinterpretation of a Higgs boson model, which also produced dark matter in a similar way. And so this new mono SBB model includes a new force media, the Z prime boson, and then dark Higgs boson. And so you can see on the Feynman diagram over here, the dark Higgs would decay into 2 B quarks, and these bottom quarks can be detected at the LHC, while it also produces dark matter, but this, of course, cannot be detected at LHC. And so by measuring the bottom quarks to detect the energy, if there's missing energy that matches what we might think of dark matter, then that's good indication that we indirectly detected dark matter at the LHC. And so when we run this model, we can produce some results. And so you can make plots of the transverse momentum and the missing transverse energy of the B quarks that we expect to see if this model were true. And so you can see the two graphs here using Pythia and Herwig inside of RECAST. And so you can see they agree fairly well. There's some slight deviations from the difference of how the two do the showering. And then we also produced a contour plot, which is a parameter scan of the possible values of the dark Higgs boson, the mass, and then the mass of the Z prime boson. And so here we can see both Pythia and Herwig. And so this is where you would expect the standard model would explain your observations. And so deviations outside of this would not be explained and would be explained by this model. And yeah, so in summary, we extended the MADGRAPH support for including custom models, and we applied this to the mono SBB model. We also separated Pythia into its new showering step and added support for custom parameters, added the Herwig showering in conjunction with this, and then we applied this model, these two showerings to the mono SBB model. We also implemented the Sherpa showering, although it has not been tested and has not been applied to a model yet. And then we also expanded documentation along the way. And so future work would be to complete the Sherpa and to actually study a new model with it. And also the future, we could also add generator support for both Herwig and Sherpa because they also include generators. And then the eventual long-term goal is to run it on Rihanna through a web interface. And here are my references. Thank you. Any questions?
Thank you, Ed.
So I'm Emily. I participated in the IRIS-HEP program under Dr. Isabel O'Halva and Dr. Savannah Thace while I was an undergraduate at the University of Texas at Austin. So today I'm going to introduce GNN tracking FPGAs, talk about CPU and FPGA data transfer rates, and give GNN runtime and estimated resource usage. So the CMS experiment at the LHC receives data at an extremely high rate, upwards of hundreds of gigabytes per second during run 2. And this rate will significantly increase with the high luminosity LHC. Because of this, sophisticated triggering systems are needed to quickly filter the data, then reduce the data down to manageable amounts. The CMS triggering system has a low-level trigger, which consists of mostly hardware, and a high-level trigger, which consists of mostly software. Charged particle tracking is a crucial but slow step in the high-level trigger. So in this project, I investigated using a graph neural network, or GNN, implemented using OpenCL on CPU and FPGA coprocessors to accelerate tracking. So FPGAs are integrated circuits composed of programmable logic blocks and interconnects. They can be fully reconfigured, which allows for convenient testing of circuit design. They're well suited for deterministic and parallel tasks, which allows for very low latency execution of tasks. They're also more power efficient compared to GPUs. However, using FPGAs comes with a few issues, such as implementation complexity and a lack of libraries. OpenCL is a widely used open source C and C++ based interface for parallel programming. It's very flexible and can therefore be used with many different types of accelerators. In this case, we're using it with FPGA. OpenCL applications are split into host and device parts. The host code can be compiled using a normal compiler for execution on CPU, and the device code has to be compiled using a special compiler. So for this project, we used an Intel Xeon CPU and Intel Stratix 10 FPGA and the Altera offline compiler for the device code. So because hits in the CMS detector are geometric, a graph made up of nodes and edges can represent the detector hits well. The basic procedure of GNN tracking is as follows. So first, the initial graph is formed from hits. Then the graphs are processed with the GNN to get the probabilities of each edge. And finally, a post-processing algorithm links the edges together into tracks based on their probabilities. So my project focused on looking at the edge classification step of this process. So the GNN has the interaction network architecture with a relational reasoning step added to produce edge weights. So there are 3 neural network models in this with their own separate weights, 6,448 trainable parameters, and the sigmoid constrains the output to 0, 1. So first, I measured the data transfer rates of our FPGA that we're using, so we can later determine if this would become a bottleneck if FPGAs are used at the trigger level. So by measuring the rates myself, I found that there is a plateau in the data transfer speed at a little over 8 gigabytes per second. And then we used the stream benchmark to measure the FPGA data transfer rates. So the stream benchmark aims to measure the sustainable memory bandwidth of a device using 4 different vector operations executed in the following order. So it's first copy, scale, add, then triad. Arrays A, B, and C are initialized with a constant value over the whole array. And we can see from these stream benchmark results that the data transfer rate for our FPGA is also over 8 gigabytes per second. So next, the current implementation of the GNN in OpenCL is shown here. The first neural network is a relational model with 3 linear layers. The second neural network is an object model with 3 linear layers. And the last neural network is another relational model with also 3 linear layers. So this OpenCL implementation of the GNN was first written by Anish Heinz, who's the IRIS-HEP fellow who worked on this project before me. And I updated it to match the current GNN architecture. So this plot shows the runtime of a forward pass of the GNN with a PT cut of 5 GeV. And these PT cuts are used to control the graph size. We can see that their neural networks have the largest runtimes in CPU overhead from data transfers, ranging from 1500 to 2000 microseconds. This graph shows the runtime. This plot shows the resource usage estimation of each kernel used in the OpenCL implementation of the GNN. You can see that the matrix multiplication kernel and linear layers of their neural networks are the ones that use the most resources. So my first proposal goal was to reduce the size of the GNN, optimize it, and implement it fully on FPGA. But we realized that this part was not possible due to the OpenCL programming model. And my second proposal goal was to analyze the performance of the GNN on CPU and FPGA coprocessors, which I did successfully. Further studies could be done with the GNN runtime and resource usage using different PT cuts and updated GNN inputs. So I say thanks to Caitlin Patterson for working with me on this project, and to Savannah, Bay, Isabel, and Gage for their help and support. And that's it.
Thank you, Emily. Any questions for Emily?
Could I ask a quick question on Emily's talk?
Absolutely, go ahead.
All right, sorry, I missed the cue.
No problem.
Emily, could you show your last slide and the second last slide? The slide that says proposed goals.
Yeah, Emily, can you bring up your slides again? Thanks.
Yep, sorry, it took me a minute.
No problem.
This one?
Yes. So could you expand a bit on that first bullet? You say it's somehow not possible because of the way OpenCL does things. What exactly is the bottleneck there?
So this on the right is the OpenCL programming model, which I took from the Kronos Group website. They wrote OpenCL. And you have to have host code that talks to the device. So like the host code will like send some data to the FPGA, and then the FPGA will carry out some operations and then send it back to the CPU. You can't take the CPU out of this process in any way because of this like programming model that they have. So it's impossible to have it fully in an FPGA.
Oh. So, okay, good. If you could go back to your proposed goals again. So then what wasn't clear to me is how you get around that.
I think we just decided not to pursue that.
But you're going to try and pursue it with a different programming model, not OpenCL, but something else, maybe?
Maybe.
So, sorry to jump in, just a comment. So we're pursuing two complementary studies in this space. So OpenCL is, like Emily said, exclusively a coprocessor based language where you have the CPU define the kernels that are executed on the FPGA. And we're also looking at fully on-device GNN tracking, where you don't need the CPU. So we're doing that with this HLS4ML package, which is a high-level synthesis language for machine learning libraries. And so that allows you to do everything fully on the FPGA, but it comes, you know, with the downside of your resource, like your space like on device is much smaller than if you do data transfer between CPU and FPGA like Emily showed. So it's hard to fit, you can't fit an entire graph on the device at one time. So you have to segment it in some kind of way, which introduces other types of complexity because you have to figure out how to like remerge the graph back together after processing it on the FPGA. So we're looking at both, and there's like kind of advantages and disadvantages of the different methods. Yeah. Got
it. Yeah, I can see trying to break up the graph and putting it back together could have overheads. What was that second one, the second framework that you say has this potential weakness? What's the name?
It's HLS4ML.
HLS4ML. Yeah, heard about that one.
Yep.
Okay, got it. Thank you so much.
Yes, thank you.
Thank you, Emily, and thank you, Savannah.
All right, so I am Jeremy Ferguson. I'm at UC Berkeley, and I am going to be talking today about my IRIS-HEP projects, graph methods for particle tracking. I was with my mentor, Daniel Murnane, at Lawrence Berkeley lab. So just some background over what I was working on for the Atlas collaboration. Studies a lot of particle interactions and collisions, and for this, track reconstruction is a critical step, but also a very slow step. And so the current methods scale roughly quadratically with the number of events that you're studying. And so going into the new high luminosity era of the LHC, they're going to need to be faster methods to complement the current methods. And so neural networks are a way of accomplishing this. So with this fellowship, I was working with people on the Exatrix project, which has a goal of developing machine learning methods and pipelines for identifying particle tracks. With this, specifically GNNs, graph neural networks, are used for this purpose because they can capture the inherent sparsity of the data, and they are also very growing in popularity. So there's a lot of algorithms and a lot of models already existing for supporting this. So what is a graph? It's a collection of nodes and edges. And in this instance, for this application, nodes are the hits recorded by the detector as particles pass through. And the edges are existing between hits that belong to the same track or particle, and they shouldn't exist between other nodes. So the goal of the whole GNN pipeline is to train a neural network to create this graph and then identify within this graph which segments of the graph belong to different particles and different tracks. So for this project, I was working with the TrackML dataset. It's some real data from collisions. It has around 9,000 events. Each one has up to 100,000 hits from around 10,000 particles. It also has some duplicate hits and noise to sort of simulate real conditions. And often I was training on a subset of that data, but I think it's just useful to get a feel for what that actual data was. So within this project and this GNN pipeline, my objective was to kind of look at how we were doing the graph segmentation for the, and ultimately to try and do track parameter regression. So this is predicting the parameters for the particle track just from looking at the nodes and from looking at the hits. However, previous attempts have not proven successful in predicting the track parameters just from the raw data in the nodes. So the idea is then to cluster all hits from each track into a single node and then predict the track parameters, because you have all the information from all of the hits in a single node, and the idea then is that you can use that to predict things about the particle as a whole. But in order to do this, it requires a clustering algorithm. And this is actually what ended up as the main goal of my fellowship and the main goal of my project, is to look at existing clustering algorithms and write a new one that took advantage of GPU operations within PyTorch, which was the machine learning package that I was using. So this is just a brief example of what a clustering algorithm does. The specific one that I was looking at sort of contracts an edge. So it takes two nodes that are connected by an edge and condenses it into one. So it preserves all the existing edges and turns two nodes into one. So the challenge then is to both do this efficiently and also to train a neural network to cluster the correct edges. And again, in this specific application, we're looking for tracking hits from the same particle into clustering them into each other, so that you end up with ideally one node per track. So there's a lot of different implementations for this. I started off looking at an open source implementation in the PyTorch geometric library. And so it's based off of this paper towards graph pooling by edge contraction. However, it's got some problems. It runs very slowly because it doesn't take advantage of any GPU operations or parallelization that the GPU can provide, because PyTorch has a lot of that functionality built in, and that became the goal of my fellowship, to write a new vectorized implementation that implements similar behavior of contracting edges, clustering edges, but takes advantage of the GPU operations. So this is the existing implementation. It scores the edges between 0 and 1 using some neural network that you can ideally trained to produce whatever behavior you want, and then sorts the edges by descending score, goes through and contracts all the highest scoring edges until all nodes have been contracted. Realistically, it won't contract all of the nodes. It will contract each node a maximum of 1 time. So if it encounters a node that's already been contracted, it'll skip over that edge. And in this way, it'll go over all the edges, but there will be some nodes left over that don't get clustered because all of the ones around them get clustered with other nodes. So the maximum contraction rate you could achieve on one iteration of this would be 50%, but in reality, it will get slightly higher than this because there will be some nodes left over. And then, of course, you can run it multiple times, have multiple layers of this contraction to get it down, condense the graph even further. So the goal of my new vectorized implementation, again, was to use the PyTorch and CUDA functionality to parallelize operations so that you can more efficiently contract the edges. However, because of this, you have to change the algorithm a bit because of how the previous algorithm functioned. You can't implement it with those vectorized functions. So I had to come up with a slightly different algorithm. So this is going to be an example of how the algorithm runs. So we have an example graph here with 9 nodes and edges between all of them, or not all of them, but edges between them and edge scores that are generated between 0 and 1. Again, just generated through some neural net, which you can later train to produce different behavior. So all these edges are scored between 0 and 1, and now we want to identify the highest scoring edge for each node. The idea here is that we want to produce the optimal pairing of nodes, but also have the most nodes getting paired up. So the challenge is to somehow balance these two goals of finding good pairs of nodes and finding as many pairs of nodes. So the first step of this is identifying the highest scoring edge for each node, and then identifying pairs of each node that share a highest scoring edge. So you see here 1 and 7 both have a highest scoring edge, and 2 and 6, and likewise 4 and 5. So once you have these pairs, you're going to remove those edges, and also because we're going to run these particular steps multiple times, we want to be able to now search for the next highest edge of the nodes that aren't clustered. The idea being that if you can't get your best possible pair, you want to have the second best possible pair, and so on. So in order to achieve this, we temporarily zero out all the edges that are adjacent to clustered nodes. So you see here, everything here that's next to a node that's getting clustered is set to 0, so that the rest of the nodes can then search for other nodes to pair up with that are unclustered. So now we do one of the other steps again. We find the highest scoring edges, again highlighted in red. But we really only care about the unclustered nodes, because if you see, all the clustered nodes are all 0 because they aren't going to get clustered again. We now find another pair, and you see here the algorithm identified a pair that it wouldn't have already identified with 3 and 8 that now share a highest scoring edge because they're one or both of their partners, or their previous nodes that they were paired with got set to 0. And now we do the same thing with clustering. And in this example, we're going to move on to the last step of the algorithm, which is creating a new graph. But you could repeat this multiple times if you had a much larger graph with more connections. The actual implementation of the algorithm that I wrote had the option of either going until you get a particular fraction of contraction. So in here, you would have 8/9 of the nodes clustered. You would set some fraction that you wanted to achieve, or just have it time out after a certain number of iterations of this, because realistically, it won't be able to cluster all of them. So you want to have some stopping behavior there. So now it creates a new graph from the clustered nodes. And you can see here that there's a lot of duplicate edges because, for example, this node represents the original node 1 and 7. and there were previously edges between 0 and 1 and 0 and 7. And so now both these edges point to the same node. So you end up with all these duplicate edges, which then have to be removed. So that's step 9, is removing the duplicate edges and taking the mean of all the edge scores. So you end up with this graph that is roughly half the size, and with all new clustered nodes that you can then do further analysis on. You can contract it again. So now let's look at the actual application to what I was looking at, the particle tracking. So I applied it to the GNN pipeline with the track ML dataset. And here I actually performed several rounds of contraction, so constructing a new graph each several different times, as well as also trying to implement track parameter regression on the clustered nodes. I was able to achieve around 60% efficiency and 60% purity. Efficiency here refers to the correct number of edges contracted divided by all edges that should be contracted. Again, it's correct if the hits belong to the same particle. So of the edges that we needed to contract, how many did we actually contract? And then purity is the correct edges contracted divided by all edges contracted. So it's a measure of how many extra edges you're contracting that shouldn't have been contracted. And I was also able to achieve a clustering ratio of around 10%, which means that the average cluster size is going to be around 10, and the track size for most particles is somewhere between 10 and 20. So it's around the range that we're looking for. But again, the efficiency and purity is not very good. It's not what we want it to be. So there's definitely more work needed there to improve the actual training and getting the contraction to work with track parameter regression. So again, the clustering algorithm can be performed multiple times. You can perform multiple rounds of contraction. And so this leads to the idea of sort of 2 nested loops. So you have the inner loop, where it's searching for different pairs of highest nodes and eliminating other possibilities. And then the outer loop is performing this over multiple rounds of clustering, so actually creating a new graph multiple times and contracting those nodes. So this is reflected in some plots that I'm about to show, where you have, just to show what the actual algorithm is doing, the outer loop by the inner loop iterations, just illustrating how much clustering is being done. So this is just an example of clustering being done over the track ML dataset. Most of the tracks would have around 10 to 20 hits. You can see here all the green and blue clusters are 10 to 15 and 15 to 20 nodes per cluster. And you also have plenty of red and black clusters here. So those are ones that haven't been clustered fully. Most likely are incomplete tracks. And you can't really tell from here where the actual tracks are going, but it just gives a general sense for how the sizes are distributed and how the clustering algorithm is performing with relation to the particles near it. And also, again, it's 6 by 6 here, so 6 iterations of the inner loop and 6 iterations of the outer loop. So here's a comparison between the implementations. On the left, we have a plot of time. So it's looking at, the orange line here is the old method of time scaling with the number of nodes in the graph. And then the new implementation, the vectorized implementation that I implemented here with a 3 by 5 outer loop and inner loop. And you can see, so there's definitely a crossover point where it becomes significantly faster, and it's just growing at a much slower rate. And on the right, to just kind of illustrate how much clustering it's actually doing to achieve this time improvement, on the top you have the old graph, which is old implementation, just running once, achieving, again, not quite 50% contraction, but close to it, somewhere between 50 and 55%, and then on the bottom, performing 35 to 45% contraction. So roughly the same amount of contraction, a little bit more, and for a much better time performance. So in summary, The vectorized clustering algorithm performs well compared to the existing implementation on time. Your specific time multiplier might vary based on inner loop and outer loop operations, but the growth rate is really the important part here. It's much faster when you get to the higher node graph implementations. And it's also worth noting that this was the time to apply the fully trained model. So this includes the rest of the GN calculations, all the other layers that are involved in the pipeline. And so again, the actual time might vary, but the salient detail here is how much faster it is when you look at higher node graphs and the growth rate as you increase the amount of nodes. So there's future work needed, again, to improve the clustering so that you can get it more efficient and accurate, as well as hopefully achieving track parameter regression to predict the tracks. And also hopefully adding in the new vectorized implementation to the PyTorch geometric library so that more people can use this clustering algorithm. And a big thanks to my mentor, Daniel Marnain, for his support. That is all.
Thank you, Jeremy. Any questions for Jeremy? No? All right. Thank you all for coming to the talks. Thank you to all the fellows and thank you to all the mentors. We have another round of talks coming up on Wednesday. Hope to see some of you there again. So again, thank you.